Okay. Should all be ready.
Mm-hmm. So I assume you can see this, but first of all, hi all. My name is Bruno Gavranović. I'm a second-year PhD student at the University of Strathclyde at the Mathematically Structured Programming Group. And I'm gonna be telling you today what I've been doing for, since I sort of started this PhD, and it's understanding neural networks through the lens of category theory. So what am I really going to be talking about? It's the information flow in artificial neural networks. And sort of what am I doing? What is the sort of overarching goal here is to understand more general cybernetic systems. And there's all sorts of things interesting. There's all sorts of interesting generalizations that this could go from here. But how am I going to do this? And it's sort of basically to take category theory seriously. Now, but this is my first time sort of giving a talk where I'm not assuming everybody in the audience knows a lot of category theory. So this is going to be pretty down to earth. It should be accessible, but please also ask questions or let me know if something is not. Also, I'm totally not sure how this is going to go in terms of time and everything. I tried, I think it should be fine, but yeah, it's my first time giving a talk sort of that's really, really down to earth. So let's hope this turns out well. Now, what really is category theory? I have like one slide just giving a brief intro, but I don't want to spend too much talking about what it is. I just sort of want to do it, and maybe hopefully it's going to be clear what that really is. But it's a language, and it's a precise compositional language at that. And I've seen the word, it's a central hub for mathematics and science. Many different fields have been people have been discovering that you can say things in the same categorical language for all these fields. And I'm just going to have like a few quotes just to get you a taste of how this style of thinking works. And this is maybe one of the more famous ones, but also it's really a nice one. It takes a bird's eye view of mathematics. It abstracts away some invisible details that we deem aren't important to spot really just these high-level patterns that we couldn't have done otherwise. And for me, I just think it's a good way to organize thoughts and a good way to write and think. Sort of, you don't really have to do CT. It's not like we're imposing these crazy ideas, but it's sort of the more you keep making your abstractions consistent and coherent, it's going to sort of look like you're abiding by these laws of category theory, if you will. And yeah, so hopefully what I'm going to say today is going to help distill some of the essence behind neural networks. So what is sort of supervised learning with neural networks in one slide? I'm just going to go through this so we're on the same page about how this works. So in supervised learning, we're sort of interested in sort of function approximation. We have a function with sort of known types, but we don't know its implementation. And we want to find out what that implementation is. And we have sort of a list of data sets. We have a list of input and output pairs. And we want to use that to figure out an implementation of the function. And how does that work with something called neural networks, right? I guess everybody knows here, since this is an AI lab, but again, we have some inputs. We process these inputs through neural network layers, and the output is dependent on a particular set of weights, and we get some sort of prediction where, for instance, if we get input of a cat, the network wouldn't be really, we wouldn't be too surprised that it thinks here it's a dog. But what we do at one point is we also have a label where we say, well, this is actually a cat. We do some sort of comparison, and well, this is a loss function, for instance. This is drawn as a box really, really vaguely now. We compute some sort of distance measure. And maybe the key 2 points here are that after we do that, we do this magical thing called backpropagation, where and this is not drawn here, but there is not just a forward information flow, but there is a backward information flow. So sort of there is two maybe patterns that we can now spot, that we have these weights, which are controlling the neural network. So there's some notion of parameterization here. And there's a second notion of backpropagation. So what is the plan for today? Having said what neural networks are, it's really just to take a bird's eye view of what neural networks are, and it's even at maybe a higher level of abstraction than what I've just told you. And if you're thinking, well, what that is, well, that's great. I'm going to tell you today. And the idea is to trace out the information flow in this picture, but sort of be really precise about what I mean. So hopefully this will all become clear as we go on. But the idea will be to spot these patterns, and there's a pattern of parameterization that we have neural networks which have some weights. And the question is, well, we can imagine, not just neural networks having weights, but some agents having their states. We can imagine all sorts of different things which have this notion in them. We have this notion of bidirectionality, namely of things, information flowing backwards and forwards. And of course, we can imagine not just errors being propagated backwards, but all sorts of things. So the idea is, can we sort of specify precisely what does it mean, what is being propagated? And can we actually say how is that related to differentiation? And then we're going to try to study how we can interact all these things and get something new. So we define all these things separately and then compose them together. So yeah, what I'm going to sort of do today is define something that's been called a few names, and it's learners, it's generalized open learners, or maybe agents. I'm not too fond of this name, but it's a name, and some sort of ways that you can do learning, sort of, and we're going to see what that means. I do want to stress here that this is early stage work. It's mostly at the moment of explanatory nature. So I find this personally very fascinating. I'm just intrigued by drawing these things, but there's sort of not anything in essence new here. I'm going to go through this talk and go through neural networks 101, but give you slightly a different spin on this, a different perspective. And there's lots of material, so let's see how that's gonna work. So again, in short, the game plan for today is to talk about this concept. What is parameterization? What does that even mean to talk about parameterization, bidirectionality? How to put these things together, and sort of how does learning work with some examples. So before I start, is there any questions about this, about the plan for today?
This all sounds good.
Okay. Let's move on then. So I'm writing here parameterization, and again, let's maybe elaborate on what I mean here. We have standard neural networks. Again, what I'm drawing here just sort of a feed-forward neural network to be simple, and just a two-layer one at that, where we have a computation, and this is the usual way of drawing it, where we sort of each node in a particular layer is connected to another by a weight, and sort of the thickness of the weight, we think of it like to tell us about the strength of the signal. But there is also another way to think about it, that this is a computation that takes an input X and computes an output Y. So it's like a map, it's like a function, but it's a parameterized function, and that because there are some parameters coming in. So let's just try to make this explicit, precise. Usually we draw maps like just functions like this. We might draw it like this. So we have an output Y, input X, and there is a map F. But here we have inputs that are sort of, and I'm gonna do something. I'm gonna just draw these inputs on top, and I'm gonna be explicit about what's happening with the information flow of these parameters, because that's gonna be important for later. So if you call these sort of weights or parameters, we can draw sort of a map that has these extra inputs. And I'm not saying much. I'm really not saying anything so far, anything of important, but I'm just sort of defining a thing that when I say a parameterized map from A to B, I'm telling you, well, you should just choose a parameter space and a function, a map that goes from parameter space P and a map that goes from P times A to B. So again, we're going to be sort of defining a bunch of things up front, and it's going to be like, okay, what's happening? And then hopefully we're just going to put them together and something magical should come out. So a parameterized map from A to B is a choice of a parameter space and this map which goes from P times A to B. Now there's fun things you can do with these maps, because it's not really important what this is, it's what you can do with this. And you can put these maps together, we can compose them. So if you, let me just see. So yes, you see here two maps, one parameterized map from A to B and a Q parameterized map from B to C. Well, we can compose them together by just drawing a box around them and getting a P times Q parameterized map from A to C. You can say some other things about these maps. For each sort of type X, we have a map from X to Y or A to C. But for each type X, there is sort of a parameterized map which doesn't do anything. We can think of it as being parameterized by just one set where there's just one element set here. There's no choice of different parameters. And it's the identity, it just doesn't do anything. And there's all these weird things I could now tell you. I could tell you that you can, oh, this just sort of moved here for some reason. Oh, I don't know why that happened. But I can tell you a few things, and I'm not going to maybe spend too much time on this.
Can I interrupt you for a second while you're sourcing the arrows? When you talk about parameters, parameter maps, are you thinking about weights, or is it something else that you're having in mind?
Sorry, yeah. So that's a good question. Yes, I'm thinking about weights. The idea will be to take these weights and sort of say them in a more abstract way. But in essence, I'm thinking about weights, about parameters of this process. If I think of this, and I'm going to have a drawing of how a neural network looks with this. Yeah.
Okay, cool. Thanks.
So yeah, let me actually just show that right now. And this is the whole point here. If I think of a neural network usually drawn like this, I'm gonna sort of switch gears and draw it like this now. So if I think of a neural network that has 4 nodes on the input, that takes a point in a Euclidean space, right? R4, and then has 2 nodes in the middle layer, that's gonna be here, and then it has 3 nodes on the outmost layer. And the weights it's taking here, like in this picture, you can't really, like the input of weights, can't really trace out the information flow, but I'm going to be explicit about that. So, if you have a matrix here or something, that's your input here, and you might have an input here. And this will be sort of weights 1 and weights 2. And the idea with these things is that it satisfies, oh, it's really all moved here. I hope the rest of the presentation is fine. So the idea is that you can just compose this map. These are associative, so you can bracket them like this and then compose the one on the right, or you can bracket them like this and then compose the one on the left. When you compose things with identities, oh, this really just moved. I'm sorry, I hope it's clear, but yeah. Let's see. I can do some magic, yeah. But when you compose things with identities, you still get the same map you started with. And so it has some nice properties. We can be precise about what it means when we compose these things. There's no sort of emergent effects happening. And some interesting thing that we can do is, if you draw them right now, we can be explicit about what reparameterizations are. So let's say we have a p-parameterized map from X to Y. And let's call that map F. Now, if we have another map from R, which goes from Q to P, which sort of takes some Q parameters and reparameterizes them to P parameters, if you will, we can compose these two maps, namely where I have here R times, and I'm going to write the identity on X. So we start with Q times X, we just apply R to get a P, and we sort of keep X as it is, which is what's evident in this picture. And then, we get a new map, which is, you can think of this as the big parameterized map. And this would be the G map. Again, I'm just sort of I'm not saying anything much. I'm just setting up the playing field. We're going to see this is gonna be useful later. But the idea about all of these things is that, if you have this sort of thing of adding parameterization or sort of reasoning about parameterized maps works for any sort of setting you might be in. So I'm drawing this as para C, right? Para of some underlying setting, and this is the whole thing with categories. It works for any sort of underlying setting. So you can be considering and any, of course, you need to be able to put things in sequence and in parallel, let's put it that way. So this works for sets, for functions, for topological spaces, for all sorts of things you can imagine. And we're going to be considering parameterized bidirectional maps. So we're going to be considering some bidirectional setting. So before I go on, is there any question about this?
May I ask a question? If you go back to the diagram just above, this one, very nice. Could you give an intuition for even considering this R? Is it change of weights during training, or what is it intuitively? Or it's not helpful to even ask that question?
Yeah, I think it definitely is. We're going to see that for actual neural networks, which are so there's two ways to answer this. First of this could be like a reparameterization, like rescaling of your weights, or it could be something different depending on the setting you're in. For instance, if you're doing with manifolds, it could be something non-trivial. But an example we're going to see of this R is going to be, and that's going to make sense in this bidirectional setting, it's going to be exactly gradient descent. So we're gonna be
so
doing,
any change of weights, is that right, Bruno? Yeah. It could be coming from learning, or it could be coming from quantization. Never mind. It's just some change in the weights of the network. Is that okay interpretation for it?
Yeah. It's any sort of thing you can stack on top, and any way you can change the weights. Yeah.
Okay, good. Thanks.
And thanks for asking these questions. Please, I might sometimes skip over something important. So this is really good.
But really, I should impose on all machine learning students in the room, ask more questions, because that will help Bruno understand what you care about. And this is kind of important because he does this work ultimately to persuade machine learning community about something, I guess. Okay.
Yeah.
Okay, cool. Just please continue. But may I encourage everyone, and if you're too shy to ask using voice, put it in the chat, and I'll tell Bruno what you're writing.
Okay, so I'll move on now and talk about, again, this other term I've sort of kept mentioning, and it's bidirectionality. Now, I'm going to make this precise right now, but sort of to motivate it again is to realize that when we draw these neural network diagrams, at least all the ones I've usually seen, we are sort of always implicit about the backwards information flow. And there's, of course, these drawings of computational graphs and how things work. But it's always been sort of, at least if not implicit, the graphical depiction has been sort of an afterthought. So what I'm going to do now is try to sort of make this again precise. And again, this might be things you know, but I'm just sort of giving it a different spin. So there is a thing called optics, very closely related to the thing called lenses, and lenses are sort of important in functional programming, they're in database theory, and these are structures which, you know, if you think about normal functions, the normal functions are just maps that take an input and give an output. These things are sort of bidirectional. So we take an input. How does it work? I have a fancy animation here where optic is something that takes an input X, produces an output Y, and saves some intermediate state S about the computation it's done. Then, when it receives an output from the environment, the red one, it uses it with the same saved intermediate state to compute, to pass back information about what it's been, about the things it's computed. So unlike normal maps, here we have 2 ports on the domain and 2 ports on the codomain. We don't have just one. So we have, so the information, as you can see, right, the information flows here and then it flows back while saving some intermediate state. And what is an optic? An optic, so we're gonna sort of be thinking about, and if you're thinking of neural networks, you know, you think of this as your input, your image of a cat, then your network computes an output. Oh, I think that's a dog. And then it saves some intermediate state about sort of, we're going to be thinking basically, maybe you can just think about this, what the input was, or it's some state. And then it receives an output from the environment saying, well, you know, this is how much you should have changed to be more correct. And then the map B on the bottom, starting from bottom, says, well, oh, I answered a cat, and this is how, so I got an input of a cat, the green thing, and I got a change, sort of, this is how much I should change, an error for that cat. Oh, this is what the input, this is how the input should be changed to be more correct next time. So it's a bit fast right now, but I'm going to explain that later again. So what's an optic? An optic is a choice of 3 things. It's this type of intermediate state. I'm here calling it M, but here it's called S, and it's also sometimes called the residual. So an optic is a choice of this state. You can, an optic between XX and YY can, you know, there's different optics with different internal states. And it has a forward map, taking an X to an out, in an input X to an output Y in this state, and a backward map, which takes sort of a Y prime and this state and to produce an X prime. So what can we do with this? Well, interestingly enough, we can compose optics. So if you have 2 optics, one going from X to Y and one going from Y to Z, we can do sort of the obvious things and then just hook them up together, where we propagate information as it says, as it's shown in this picture. And again, you might be sort of seeing this. I'm just saying the things you probably already know. This is what neural networks are doing with backprop. You have layers which compute forward information, they save some state, and then given some errors in what they computed, they backpropagate this error backwards. And there's a few things you can say, right? For each, you know, pair of objects like this, there is an identity optic which doesn't do anything. It doesn't matter which way you compose them, and bracket optics, and there's all these sort of nice properties, very simple but nice properties. And so again, what does this allow you to do? It's one of the things you can do is sort of reason compositionally about automatic
Bruno,
differentiation.
may I interrupt you? There was a question. There were 2 questions, but one is really about this slide. From
yeah.
James.
Oh, I see. Yeah.
Yeah.
Oh, does X still mean input? Yeah. So yeah, if you're talking about this X prime, right. So I'm thinking of this here as, if you have an input X, say a cat, this is going to be we can think of this as a change, you know, some sort of notion of a change, of a tangent. So, and precisely here it's an output, right? So the arrow is going the other way because we pass information this way, but we propagate the errors backwards. I'm not sure if that answers your question.
Okay, does it help to think that in machine learning we simply don't visualize the corrected image, so to say, or the image that's backpropagated? We stop somewhere in the intermediate layers because we're not interested in that X prime on the on the very inner layer, on the first layer. But basically, otherwise, that's what's happening. I think that might be what's causing confusion, right? Because in machine learning, we're never saying, oh, I propagated this forward and then I propagated backwards, and that's what my image is. So we don't really see this X prime, but this X prime is implicitly there in our analysis. Does that help to say that? Or is it even correct to say that?
No, I think you're right, and there is definitely interesting things here, right? We can think about there's sort of two ways we can think about it. One of them is as propagating just gradients changes, and one of them is, as you said, to think about sort of, well, what is the more correct image? What is the more correct cat or something like that would be like deep dreaming that's happening.
Yeah.
And you could think about it here, but I guess what I want to say is at this point, I'm sort of not making a distinction. Optics talk about they're not really saying they're not giving you an interpretation of what these things are, but I will later on, and maybe that's gonna help. So yeah, I'm not thinking of it as the more ideal input. It's more of well, I think it was the best strategy here because I will be talking about it actually. So I'll be make some distinctions. So maybe James, if that doesn't make sense later, maybe I can answer. But the thing is, I'm just gonna say briefly now, you can think about it in sort of both ways. And I haven't told you which one is it. You can think about it as propagating changes, but you could also think about it as which is the more ideal input. And both of them are right. And I'm gonna take one of these perspectives and sort of study it a bit more. Yeah, no worries. I also see I missed the other question about extending to other ML techniques, and I think maybe that's a good question for the end when I tell you what the whole thing, and we can talk about future work.
Yeah, that sounds like a good plan.
So yeah, hopefully this thing with the X prime and changes is gonna make sense just now. You can certainly think of it that way, yeah. So, and yeah, actually, there's two different interpretations about this, so I should be clear about that. And again, we're gonna talk about that. One of them is when you're doing differentiation, when you're propagating back gradients, and you can reason compositional about it. Now, I'm not gonna go in depth about that. Also, I'm seeing sort of time, so I might just sort of speed up just quite a little bit. But just to be clear, I should aim to finish at like 5 before 10 or something.
Yeah, it's okay. Sometimes they overrun, and that's fine. Some people may leave,
Okay.
and others more interested may stay. Go what makes sense. There's no point to rush.
Yeah,
If you lose the
I
audience,
know.
that doesn't make any good anyway.
Yeah,
Okay,
I
just
know,
let's see how it goes. But yeah, at 10, some people may just start disappearing, in which case they'll catch up on YouTube later.
Right. So I'll briefly say here about one possible choice of these residuals, about this internal state, if you will, for optics. And it's hopefully clear from the left picture here, but you can sort of choose this internal state to be the type of the input X itself. And we can imagine sort of just copying what the input was and saving that for the backwards pass, and sort of factoring out the top map with with something that's called in lens terminology, the get and the put of a lens. So, we think the get of like getting stuff out, and the put is sort of putting stuff back in. And I'm not going to be focused too much about these internal representations, even though I might use occasionally this one. But it's to make it's sort of just to make clear that this is a thing called lenses, and there's all this it's interesting terminology about lenses and optics. And the idea is, why is this called also lens and optic? I probably should have said that before. Is that if you think here of having like a big thing, you can think of this as sort of zooming in on a small part. If I think of the image of a cat, this zooms on the answer, like this zooms on the concept of what that is, and then I might give you a way to change that from a cat to a dog, and then hopefully this change might be propagated back into the big image. Again, there's all these various different perspectives here, but it's just important to remember the terminology for now of just lens. And there's a paper that talks about the simple essence of automatic differentiation, sort of in this language. So it seems more in functional than in categorical language. But anyhow, examples of optics and lenses, as people ask. So one of them is backdrop, and I'm going to get to that. But the other one, I'm going to get to that in the future. But the interesting one is that optimizers, you know from machine learning, are sort of optics. So if you remember what gradient descent is, we think of it, we have a particular function, and for a particular point, we might be moving downwards on the slope, and we're doing some optimization. So we can write this map as and this map is something that takes a parameter and a change in that parameter and computes a new value of that parameter. So I'm saying here P, and I'm being sort of just syntactically writing delta P, and then saying, well, you just take P and go in the alpha multiply the change by alpha and go in the negative direction of the slope. So interestingly enough, we can frame this, and it's pretty interesting to frame this as a lens. So gradient descent, we can think of a lens that goes from here PP to PP, which is identity on the forwards. So the forwards map just doesn't do anything on the parameters, but the backwards map, when it gets a change in the parameters, it uses so this would be our change in the parameters, delta P, and we use that with the current value of the parameters to produce a new parameter value. And this map U is precisely this one. So what I'm giving you now, maybe hopefully this makes some things clearer, is that here you have a change in a parameter. Here you're actually computing a new parameter value, and you can sort of pack this up as a lens. Now, optimizers in machine learning, there's more of them. There is not just gradient descent, there is momentum, there is nester of momentum, and there's all these things, and they have sort of additional state. So they don't have just parameters, they have some state here. And it turns out all of them can be formalized as lenses. And that's I find it very interesting. And I'm not going to go into detail about what happens here, but I can go there later if you're interested in it. And even though if you're thinking here that this is just not doing anything on the forwards part, well, why is that a lens? It actually turns out nester of momentum and some of the other optimizers are doing something non-trivial here. So it's sort of justifying the idea that we should be using lenses here. So again, what am I doing here? I've told you about these optics, how you can compose them, and I've told you about categories. And category theory is all about defining precisely structures. And if you haven't heard about categories before, I'm going to tell you that you already know two, and it's para and it's optics. And given the constraint of time, I'm just going to say it's a network of relationship and some properties you have. So you have some objects in these categories, you have ways they're related to each other. And the main idea is that categories themselves, we want to think of them as first-class objects. So if we have one category and we have another one, we want to map between them. And now these categories are objects in some other category. And the idea is to just juggle abstractions around in the mode, whatever is the right level of generality. and be precise about what properties are preserved. So I'm now going to tell you about the main thing from today is that when you put these things together, you get something very interesting. When you put parameterization and bidirectionality together, so if you start with some base space, maybe sets, maybe differentiable functions, maybe topological spaces, when you do optics on them, so we think about bidirectional maps, and now we think about parameterized bidirectional maps, we get something interesting that could be interpreted as learners. So let's unpack what that means. Now, what's a parameterized optic? Well, I've told you, a parameterized optic, starts from an X. And I'm just using some letters here. There's lots of them, but I'm going to explain. Starting from some XS, producing some YR, but being parameterized by some parameter space. And now that has to be a pair as well. And the map F goes from, if you remember how para was defined, from P times X to Y, right? But here it's optics, so it's all of this stuff. It takes a P times X as input. And actually, I might just go through this might just go through the drawing while I'm explaining you what this is. So there's lots of letters here, and it might be slightly confusing to think about what's happening, but we're going to be thinking of these as sort of parameters. So, and if you remember how I've drawn an optic before, which was like this, now we're going to do the same thing. And again, but spoiling, have parameters flowing in on top and maybe co-parameters or something like this flowing in on the bottom. So how do I think of this? A neural net, we can think of this as a neural network. It gets some input, say a cat image or something, and it uses some current parameter value, current weights of the network to produce an output. Hey, this is 20% probability of a cat and something like that. Then it awaits, it sends that back to future, maybe there's other layers or something, right? We can hook them up like this. But the idea is it waits for an output from the environment to say, well, and the environment might say, well, this is how much you should have changed. This is the error on your answer of this cat. And then it uses the saved state, which is sort of might be just remembering what the input was, to produce a change in parameters and to backpropagate a change in the input. So, if you hook up a few layers, this is what backprop would be doing. So an optic here is, as I said, it's a choice of a residual. It's some M, and it's the map here called left, which is the map, basically the one I've called top before. So maybe I'll just do that right now. I'll just call them top and bottom like I did before. So it takes a parameter, a weight, it takes an input, produces an output Y, and saves some intermediate state. The bottom map takes that intermediate state, gets a change and computes, sends back a change into S, right, into the previous layers, and a change in parameters. Now, notice that here we get automatically 2 parameter ports as opposed to 1. So we have an input parameter and an output parameter. And this sort of just magically came about of defining these things precisely before. And very interestingly, our reparameterization now isn't just like a normal map, which just scales up the weight space. It's an optic in itself. So I'm just drawing this here in a funky way. But maybe let me give you more intuition, right? I can draw this parameterized map like this, like here. So by the way, I've drawn it in a multiple ways, and I might be switching all these abstractions now, so if it's not clear, please ask. But you can think of well, you can draw this map in this way, where I sort of take this Q and make it go back on top. And the idea is when you reparameterize things, just like before, when you stack things on top, you can just think of this as a big learner that encapsulates this. But now it's doing some bidirectional change here. And I'm not going to worry too much about the left image for now, but I'm gonna actually skip to some interesting bit where let me think about how to do this. Yeah, so so before I do that, give me a second. So yeah, I'm thinking, given time, I'm going to do the following. I'll briefly tell you how gradient descent as a reparameterization fits in all these things. And I'll go briefly through just what this differentiation means in the context of neural networks, and about how you can automatically construct the backwards pass from the forwards one. This is a whole area of study, and it's possible to talk about this in really detail, but the idea is, you know, you can make this more precise in some language. So you know what, I'll just go here. So again, I'll make a thing very precise, and maybe skip through some of the math. We can, and give you just an example. We have a linear layer. So let's consider a linear layer in smooth spaces where we take a real number and produce a real number out. And it's parameterized with two numbers. So it's like there's weight 0 and weight 1. And this is going to be our parameterized map. So it takes two weights, an input, and it sort of just does the simplest thing. We have like a bias term, and we scale up the input. Now, we can think of this input as going here. This R2 is sort of scaling this up, adding the bias, producing an output. We can, and then we can talk about something called, you know, the reverse derivatives and all that stuff, which is basically saying, and this is the standard notion of differentiation, just framed in a different language, which is saying, well, given this, given the parameter weights, given the input, and a change in the output, I can just differentiate. And I'm basically maybe just being precise about what it means to do that in the context of this para-optic and all that stuff. And telling you that when you get an output here, you know, if you just unpack this, you're going to get some particular change in parameters. And what is that going to sort of allow us is that, again, I'm sort of reframing these things and maybe jumping too much. I'm realizing there was maybe a better way to say something before, but the rough idea being, and Ekaterina, this is what you asked about before, is what is this reparameterization doing on top? And I guess I want to say one thing is that this reparameterization now, if you think about this in the context of neural networks, will be gradient descent itself. So if you remember, I've told you reparameterizations in this bidirectional setting are going to be optics. And I've also told you a gradient descent is an optic. So it's going to turn out that gradient descent is going to be some sort of a reparameterization here. So if we think about, and I'm going to sort of do two things in parallel, I'm going to do two things in two different ways here, and hopefully it's going to be clear what's happening. And then I might just skip on to the examples after this. So I've said a few times already that you can think of a neural network with inputs flowing here and its weights coming here, and you can draw them in this particular way. So if we have an R here, it's a number, and then and this would be R2. And then I've said how you maybe want to consider sort of a linear layer where you add the bias term and multiply the input X and compute some output R. And this is what's happening here in this language. Now, then that output R is going to be processed in the rest of the network with the loss function and so on. And we're going to be getting sort of an error back. We're going to be getting, hey, you know, this is how much you should have jiggled your parameters to, this is how much you should have changed your output to be closer to what we wanted. And this is the thing you receive here. And then after you do that, the network internally can say, well, you know, I can do partial differentiation, and given where I was, so this would be the state. can compute an output, and given where I was, I can compute a change in my inputs and sort of backpropagate that error to the previous layers. But I can also compute a change in my parameters. I can figure out how should I have changed my parameters as to be closer to what the correct answer was. Now, it turns out that the gradient descent thing I've drawn before, right? If you remember, I've drawn a lens like this, which has an update. So I've told you, there's a parameter coming in. Its identity, it doesn't do anything. And then when it receives a change on the bottom, it uses an update with the current parameter value to produce a new parameter value. Well, it turns out this is precisely a reparameterization you can stack on top. So you can well, I've just drawn this bad here. I'm just going to draw it again. It's precisely a parameterization you can draw like this. So this would be the U map. So this was quite surprising for me when I was also sort of understanding these things, is that you get this different perspective on how learning works and how maybe gradient descent can be thought of as a reparameterization. And I'm drawing it another way here, where you get an input in the parameters, you sort of pass it on to the network, and you save this state. And then when the network produces a change with the current parameter value, you produce an output. Anyhow, I'm sort of realizing I jumped through many things, and please feel free to ask.
Actually, it's
Please
okay,
feel,
and it does make sense. Actually, Bruno, don't worry, you're doing well.
Okay.
Maybe you skipped something confusing, but we didn't see those confusing things.
That's great.
It still makes sense.
That's great. Yeah, I might just keep on and just well, before I go to examples, I might. No, I think it's near 10, so I might not even ask for questions. I'm just going to give you some examples and a flavor of what these things can go into and how you can think about some actual neural networks in this way. So the idea is, we can think of a learner or a neural network as a blue box here. We take some inputs, and we can think about optimizers as a thing you stack on top. Now, a neural network gets, and we can immerse this neural network in some sort of environment, a state and a co-state. It doesn't matter what these things mean. And now I'm going to just tell you some examples. First of them is like a vanilla neural network, vanilla training, where it's just any neural network and you do gradient descent on top. And there is something with loss involved here, which I'm going to skip over. What you can do is you can do autoencoders, which you probably know about, right? Which I have an encoder network and I have a decoder network. The encoder network takes an X and computes, this sort of compressed representation Z, and then the decoder takes that Z and tries to compute back X. And both of them use gradient descent. So we can think about this network that just trying to minimize some notion of a distance between the input and the recreated one. Now, we can draw GANs in this way, and they are actually quite similar to autoencoders, where I have a generator G, which takes some latent vector and produces an image, and I have a discriminator which takes this image and produces some sort of valuation, and they're both parameterized. So we can, a GAN itself is a learner, and it's a composite. So it takes either, and that's interesting here, it takes either an image or a latent vector. And then if it gets an image, it doesn't do anything and just passes it on to the discriminator, which produces a value, and then it's back propagating. But if it receives a latent vector, then it's using the generator, and then that is being passed on to the discriminator, which is going to say, hey, is that real or fake? And we're training the generator with gradient descent, and we're training the discriminator with gradient descent. Now, when you're drawing it like this, and when you get into details, it turns out that this thing is a learner in itself. And this big box, the optimizer, is a product of optimizers. And you might ask, well, can we just have gradient descent since it's a learner? Can we merge this optimizer in some way? And I should one time I can go into more detail about how this competitive gradient descent works, which is like a more fancy optimizer for GANs. And very surprisingly, when you frame these things in this particular way with reverse derivative categories, it turns out that you can do differentiation on Boolean circuits in exactly the same way I've described, well, in a meaningful way, but using the same framework I've described so far. So you don't have to learn with smooth numbers. You can just sort of jiggle bits around and change them in a way that could be said is differentiation. And maybe I'll just stop here at future work and just tell you all these possible things you can branch off from here, which is I'm trying to understand goal-directed behavior and basically put this is talking about basic neural networks. There's nothing sort of very very interesting yet here coming out, but I'm really interested in exploring things such as meta learning, connecting using this category abstract language to connect the AI stuff, which is happening with neural networks, with things that are happening with automata learning, which is very interesting, trying to learn what automatas are based on interactions. This is very much related to game theory, and these are all open dynamical systems. And there's all this stuff that this can, all these directions that this can branch into. But for now, I'm gonna say thank you for listening, and yeah, ask for any questions.
Well, thanks a lot, Bruno. It was a great talk. It was really pleasing, your final two examples, when you also showed how autoencoders and GANs are also fitting within this analysis. So that's really nice. It's very good. Are there any questions? By the way, there is Daniel here in this room who's a true expert in autoencoders. You may want to talk to him at some point. Questions? John stayed until the end, which is a miracle, but he's not asking questions. And let me stop recording, by the way, so that everyone could relax and just ask questions.
Okay, well then,